this video is going to be the additional practice problems for Chemistry Chapter 5. And we're going to start with number 1. And number 1 has A, B, C, D, and E parts, but then there are questions related to each of those, questions 2, 3, and 4. So we're going to, for each one in number 1, we're going to go ahead and answer questions 2, which ask us to draw the stick figure, question 3, which asks us whether it's polar covalent or purely covalent, and then number 4 asks whether it would dissolve in water. So for each one, we'll go ahead and answer all of those questions. Okay, so number 1A, the molecule is CF4. Okay, so we'll start with the Lewis structure. So carbon has 4 valence electrons, and then we would have 4 fluorines, each of which have 7 valence electrons because they are in group 7. Fluorine is group 7 on the periodic chart. So it has 7 valence electrons. Okay, so it should be, maybe you can start to see that carbon has 4 unpaired electrons and each fluorine has an unpaired electron. So we would just match up each fluorine with the unpaired, each unpaired electron on the fluorine would match up with an unpaired electron on the carbon. And we'll draw those lines to indicate that the 2 electrons are shared. Okay, so that would be the Lewis structure for CF4. So then let's go ahead and do number 2A, which asks us to draw the stick figure. So carbon's going to be our central atom. We look at it and we see that around that carbon there are 4 bonds of 4 electrons, and every one of those electron pairs is bonded to something, so that makes its shape tetrahedral. And this is the way that we draw a tetrahedral molecule. Okay, so it's tetrahedral. And then we are asked in number 3 whether it is polar covalent or purely covalent. Polar covalent, and so polar covalent would mean that even though the molecule as a whole doesn't have a charge on it, there are charges within the molecule. So to do that, we need to look at the 3D structure. We need to look at the stick figure. And another word for purely covalent is nonpolar. So you can use the word purely covalent, or you can use the word nonpolar. So in a tetrahedral molecule, the fluorines are going to pull, they're going to have a greater pull on those electrons than the carbon because they're farther to the right than the carbon on the periodic chart. However, in a tetrahedral molecule, the pull that those fluorines, it would be equal in all directions, and therefore that makes this a nonpolar molecule. Okay, then we will look at number 1B. Okay, so phosphorus has phosphorus is in group 5A, so it has 5 valence electrons. Hydrogen has 1, and then we have 2 chlorines, and each chlorine is going to have 7. Okay, so again, the phosphorus has 3 electrons that are not paired with anything, and the remaining atoms also each have an electron that's not paired, so we can just pair those up. So one would be a hydrogen here, so we can get rid of that. Take one of these chlorine, this chlorine, and this can share. So we'll have those share and put a chlorine there. That gets rid of that one. And then we'll pair up this one and this one to make a bond, and we have the chlorine there. Okay, so that's our Lewis structure for this compound. So then we look, and around that phosphorus, you see that there are 4 electron pairs. But one of the pairs is non-bonding. Okay, so this pair is non-bonding. So that means that our shape then would be a pyramid. Okay, so we'd have the P in the middle. There's no bond on the top, but we would have a chlorine here. Chlorine here, and then to indicate the one that's going back, we would put the hydrogen there. Okay, so that's the stick figure for a pyramid shape. So then we ask, then the next question is it polar or non-polar? So the chlorines are going to pull harder than the fluorines or the phosphorus, and the phosphorus is going to pull harder than the hydrogen. So you're going to have unequal pulls within that molecule, which makes it a polar molecule. And then will it dissolve in water? Polar dissolves in polar, so yes, it will dissolve in water. Okay, number 1C. So Te is tellurium, and then I2. So tellurium is number 52 on the periodic chart. So if you find number 52, you'll notice that it is a non-metal, so this is going to form a covalent compound. So we'll put tellurium in the middle because it is in group 6A, so it has 6 unpaired electrons. It has 6 valence electrons. And then we would have 2 iodines, and those are in column 7A, so they will each have 7 valence electrons. So again, we have 2 unpaired electrons here on the tellurium, and each iodine also has an unpaired, so we'll just pair those up. The one iodine will go there, the other iodine will go here. And then do remember, I think I forgot to do this on the others, but remember to put the rest of your the paired electrons on your Lewis structures. Okay, so that's the Lewis structure, that one. And so then let's go ahead and draw the let's go ahead and draw the 3D figure, the stick figure. So we look at the tellurium and we ask how many pairs of how many electron pairs are around the oxygen, and there are 4, but two of them are bound to something and 2 are not. So that tells us then that the shape is bent. So 4 electron pairs, but 2 of them are non-bonding pairs. So the bent shape would be, the 3D model would look like this. And iodine is going to have a greater pull on those electrons than the tellurium, and they're only pulling in a downward direction with nothing to counter in the upward direction. So that means that there's unequal pull, and so this would be a polar molecule. And polar dissolves in polar, so yes, this molecule would dissolve in water. The next one is Se squared, or Se2. So Se is selenium, and selenium is in row 6, so it has 6 valence electrons. And we have another one of those. Okay, so each of these has 2 electrons that are not paired. So we just need to match, we're going to need a double bond, so we'll put these 2 together, and we'll go ahead and we can put them here and make a bond there, and then we'll go ahead and put this one and this one together, also making a double bond, and so we would have that. Okay, and then around this selenium, you'll go ahead and put the pairs of valence electrons. Now we could have drawn this like this, it would be the same thing. Okay, that's the same thing. So this shape is considered linear, and because these are the same atoms, neither one is going to pull any harder than the other one, so this would be a non-polar molecule, or purely covalent. It's the same, purely covalent means the same thing. And non-polar does not dissolve in water, so it will not dissolve in water. Okay, so that completes number 1D. So then let's do 1E, and 1E is C. And I know this is not real clear on your paper, but it's an I. So CIP, carbon, iodine, and phosphorus. So carbon has 4 unpaired electrons, so it's going to be our central atom. Iodine has 7 unpaired. And then phosphorus has, it is in phosphorus in column 5, so it has 5 unpaired electrons, or it has 5 valence electrons. Okay, so let's go ahead and start by pairing up these two here. Okay, so that takes care of the iodine. And then we have 3 here on the phosphorus that are unpaired, and we have 3 on the carbon. So what we can do with those is we can make a triple bond over here with those ones that are unpaired on the phosphorus and the carbon. And so then we get this. Okay, so let me draw that a little bit neater here. So you'd have the phosphorus with a triple bond binding the carbon, and then that carbon bound to the iodine. Still have the bound pair for the phosphorus up here, and then you'd still have the 6 paired electrons around the iodine. Okay, so then we look at this, and is phosphorus or carbon going to have a greater pull? So phosphorus is 1 down, but 1 to the right. It's lower, but it's to the right. So those would actually have the same pull. If we look at this one's a little bit tricky. So if we look at the chart on page 138 in your book, we say that the electronegativity for phosphorus is 2.1 and for carbon it's 2.5. So carbon actually is going to have a bigger pull on those electrons than the phosphorus. And then if we compare iodine and carbon, carbon is 2.5 and iodine is 2.5, so those are going to be the same. Okay, so no pull there. So again, because we have the carbon pulling in one direction, but these are they're not going to get really, they're going to share these equally. That's going to make this a polar covalent molecule. So we know it's linear because the carbon is pulling in one direction, but not pulling in this other direction. No pull here. That's going to make it a polar covalent molecule, and it will dissolve in water. So then if we look at the so its shape would be linear. So we would draw this exactly like that. It's a linear shape. It would be a polar covalent molecule. Okay, so that takes care of numbers 1, 2, 3, and 4. Okay, let's look at number 5. And number 5 is asking us to name these compounds. So the first one is CaCl2. So the first thing you should notice about this one is this is a metal and this is a non-metal. So it's an ionic compound. And when we name ionic compounds, we just name them the first word. The first one we just give it its name, and the second one we put the ending "ide" on it. Okay, so that is calcium chloride, ionic compound. Okay, number 5B is this. Okay, so we notice first of all that it is covalent, And so we would put a prefix dot before each word, dinitrogen, monoxide. So we use the prefix mono with the second one, but if there's only one of the first one, we would not use the prefix. So it would be dinitrogen monoxide. Okay, the next one is SO3. Okay, so S is sulfur, and we don't, even though there's only one with the first one, we wouldn't say monosulfur, because we don't, if the first one just has one, we don't use a prefix. And then the prefix for 3 is tri, so it would be sulfur trioxide. So that one. Okay, next is N2O4. Okay, so there's 2 nitrogens, so that's dinitrogen. And there's 4 oxygen, and the prefix for 4 is tetraoxide. Okay, dinitrogen tetraoxide. Okay, next one is C2Cl2. Okay, so C is carbon, and Cl is chlorine. 2 carbons, so this would be dicarbon. They're both nonmetals, so it is a covalent compound. Dicarbon dichloride. Okay, I don't remember if number 6, and I know this may not be on your sheet, but we'll do it anyway. We're given a list of elements, and we are asked to place these from lowest to highest electronegativity. Okay, so for that, we're going to look at the periodic chart, and the ones that are farthest to the left and lower would have the lowest electronegativity. So we'll do calcium there. Then let's see. Looks like Ga might be next. So we're moving to the right and toward the top. We're looking for the ones that are to the right and to the top. So rubidium, Rb, let's see, where's rubidium? Actually, rubidium would be before calcium. So we put Rb over here, rubidium, calcium, and then we're just looking at phosphorus and oxygen. So phosphorus is lower and to the left, so it would be P and then O. Okay, so this would be lowest electronegativity, and oxygen would have the highest electronegativity. So again, for electronegativity, the closer they are to the right and to the top, we would have the higher electronegativity. Okay, number 7, we're just asked to determine the shape of a molecule of Cl3. So phosphorus trichloride. So phosphorus has 5 valence electrons, and each chlorine is going to have 7. So basically, each chlorine is going to have 1 unpaired electron. Because we're going to have 3 of these. I guess I'll go ahead and draw them so you can see. Okay, so each chlorine has 1 electron that is unpaired. So in each of these, each spot on the phosphorus, we can move a chlorine and they can share those unpaired electrons. Okay, so that's what the Lewis structure would look like. And then if we draw the shape, so we have 4, the carbon has 4 pairs of electrons, and 3 of them are not bonded to anything. So that would mean that it is a pyramid shape. So a pyramid would be like this, a triangle showing that it goes forward, and then to show that there's one going back. So in a pyramid, you would not have one on the top. So this is a pyramid. Okay, that's number 7. Number 8. Determine the shape of an H2 molecule, so dihydride. So each hydrogen has 1 unpaired electron, so they're just going to share those. So this would be the shape, and this shape is linear. Doesn't matter how you arrange them. You can arrange them like this, but it's still just a line. So that is a linear molecule. Okay, number 9 is S-silicon tetrachloride. Okay, so the silicon is in group 4A, so it has 4 valence electrons. Chlorine is in group 7A, so it has, each chlorine will have 7 valence electrons. So you should begin noticing now that there's 4 chlorines, each with an unpaired electron, and silicon has 4 unpaired electrons. So we would just pair each of those chlorines with the unpaired electron on the silicon. Okay, so that's what the Lewis structure would look like. If we drew the shape, we'd have the silicon. It's tetrahedral because the silicon has 4 pairs of electrons, and none of them are unbound. All 4 of them are bound. So it would be this, and this, and then the one up at the top. Okay, so this is tetrahedral. Number 10, what is the shape of H2S? So this would be a dihydrogen sulfide molecule. So again, we have 2 hydrogens. They each have 2 electrons, and the sulfur has 4. Okay, so we can have these 2 shared, and we can put this and this together to share, so we'll have a hydrogen there. And then we put these 2 together. Okay, so that our shape then ends up being this. The hydrogen there, and then, okay, so if we look at this, we have the sulfur one. Oh wait, this needs to have 2 more unpaired electrons there. Okay, so the sulfur has 4 pairs of electrons, but 2 of them are unbound. Okay, so that means that its shape is bent. Okay, so we'd have the sulfur here, and we'd have each of the hydrogens there. And then we draw there, when we draw the shape. Okay, so that is a bent molecule. Okay, number 11, determine the shape of CS2. Okay, so that'd be carbon disulfide. Carbon has 4 valence electrons, and sulfur is in group 6A, so each sulfur is going to have 6. Okay, so the only way we can arrange those 2 is we can have these 2 share with these 2. Okay, so that means it's going to need to be a double bond. They're going to need to be moved into the middle. And then we'll have these 2 shared with these 2. Put that bond on the other side. And then go ahead and draw the other pairs of electrons around that sulfur so that it has 8. Okay, so now the sulfur has 8 and the carbon has 8. So this shape is linear. And the sulfurs will pull on those more than the carbons, but because you get pull in both sides, it would be a non-polar molecule. Okay, that is number 11. Okay, let's do number 12. 12 has multiple parts, and what we are asked to do in 12 is to say whether it's ionic, polar covalent, or purely covalent. Remember, another word for purely covalent is nonpolar. So for the covalent molecules, we'll have to draw the we will have to draw the stick figures to figure out whether they are polar or non-polar. Okay, so let's start with A, MgCl2. Okay, this is a metal. This is a non-metal. So this is an ionic compound. Ionic molecule. Ionic compound, same thing, okay? And we would, so the name of this would be magnesium chloride, as it's ionic. Okay, number 2 is CF3Cl. Okay, so let's start by drawing the Lewis structures. So carbon has 4 unpaired electrons. Each fluorine is going to have 1 unpaired, or it will have 7 valence electrons, so 1 is not paired. You're going to have 3 of those. And And then you'll have a chlorine also that has 7 valence electrons. Okay, so again, hopefully you're beginning to see that we can pair the unpaired on each fluorine with an unpaired on carbon, and then the unpaired on chlorine in the other spot. Okay, so these two will bind up together, this one and this one. So we'll put a fluorine up there, this one and this one. So we'll put a fluorine over there. And then that just leaves this and this to make a bond down there with the chlorine. Okay, so it's a little sloppy, but get my eraser going. There we go. So this is what it would look like. Putting an F on that fluorine, or FL. Okay, so and then so let's go ahead and just redraw this so you can see more neatly. So you have 3 fluorines bound to it and 1 chlorine. And then you would need to draw the other paired electrons around the fluorine, so you make sure that you show that it has 8 valence electrons, and the same thing with the chlorine. So now everybody has 8 valence electrons at least some of the time. Okay, so then let's look at the shape. So the carbon has 4 pairs of electrons around it, and all of them are bound. So that means it tells us that it's tetrahedral. So we'll put the carbon in the middle, and we can draw a fluorine here and a fluorine there, and then our little triangle for a fluorine, and then we can draw our chlorine like this. Okay, so that's what the tetrahedral molecule would look like. And then to tell whether it is polar or nonpolar, we have to look at those bonds. So fluorines are going to pull harder than the carbons, but and also the chlorine will pull harder. However, fluorine is higher on the periodic chart than chlorine. So the fluorine will have a greater pull on those electrons than will the chlorine, and that's going to make it a polar molecule. So you have unequal pull of electrons, unequal sharing of electrons, so that makes it polar. Will it dissolve in water? Polar molecules dissolve in water, so yes, it would dissolve in water. Okay, next is CS2. Okay, so we have a carbon. Some of these we've already done, and we just didn't name their. Okay, so then we have 2 sulfurs, each of which is going to have 6 valence electrons. So we've already done this one, but we'll do it again. Okay, so for this one, we will need double bonds with the sulfur, the carbon and the sulfur. The sulfur is going to have it will pull on those electrons harder than the carbon. So it will have the electrons more of the time than the carbon. So this is linear, and it would be nonpolar because you're going to get equal pull in each direction. So it's nonpolar or purely covalent, which means that it would not dissolve in water. Okay, H2, again, we've already done this. H2, so you'll have 2 H's, each with an electron. They'll share those. So that's linear. and either one, because they're the same, neither one is going to pull any harder than the other, so this would be nonpolar, so it would not dissolve in water. Okay, next is the silicon chloride. So silicon tetrachloride. So silicon has 4 unpaired electrons. Each chlorine is going to have one that has 7 valence electrons, and one of those is not paired, so it will have 4 of those. So I'll go ahead and draw them. But hopefully it's clear to you that we can just put a chlorine on each side, pair up a chlorine, the unpaired chlorine, with an unpaired silicon, and we get this molecule. Okay, so that's the Lewis structure. In terms of its shape, the silicon has 4 pairs of electrons around it, and they are all bound. So that means that it's going to be tetrahedral. So we'll have a chlorine there, one up there, and then one like that. And chlorine is going to pull on those more than we'll have a greater pull on the electrons, but you get equal pull in all directions. So that means this is nonpolar. If it's nonpolar, it will not dissolve in water. Okay, then the last one is PCl3. PCl3. So the phosphorus is group 5, so it has 5 valence electrons. And then we have 3 chlorines, and each chlorine is going to have 7 valence electrons. Okay, so again, 3 spots on the phosphorus that don't have a paired electron, and each chlorine has an unpaired electron. So we will just pair up a chlorine with each of those unpaired electrons on the phosphorus. So that takes care of those. Go ahead and draw the so phosphorus has 8 valence electrons. We need to go ahead and draw the other 6 on the chlorine so that you can show that the chlorine has 8 valence electrons at least some of the time. Okay, and then you can look who's going to have the greatest pull. Chlorine is farther to the right and higher. No, it's just farther to the right. So it will pull on those electrons with greater force. If we look at the shape, phosphorus has 4 pairs of electrons around it, but one of those pairs is unbound, so that means it's going to be shaped like a pyramid. So we put our phosphorus here. In a pyramid, there's nothing sticking out on the top. So we have a chlorine here, we'd have a chlorine here, and we'll have a chlorine here. And so we have these things pulling downward, but nothing's pulling up pulling in an upward direction to balance those out. So that would make this a polar molecule, and it would dissolve in water. Okay, so that finishes up the additional practice problems for Chapter 5.